Okay, so I'm going to prove that to every relation corresponds a Galois connection. Okay, now let's have a relation on P and Q. Okay, where P and Q are opposites. I'll represent them like this. Okay, they're partial orders, they're not total orders. So I keep in mind that, for example, A is smaller than A. I don't bother to write it like this, but you'd usually write it, sorry, I don't bother to write it like this, but you'd usually do that. Okay. Now, what's the Galois connection here? First, let's just take a bit of a tangent here on something that seems different. Obviously, if we have a relation, by the way, a relationship will be like, for example, PQ might be true, right? Now, obviously, we will have that, for example, for every, how should I write it? Let's write it like this. Okay. Obviously, for every P, we can, this is not a statement, but we can write RP, which will be equal to all Q such that P R Q. Okay, it's a very natural thing to do. Okay, and obviously P is in capital P, our Q will be in capital Q, but also for all Q, we can write the set of all P that are related to Q. Okay. Now our adjunction will come from this. Okay. Here's what we're gonna write instead. We're gonna define this function. For say we have a set. Let's say for all A subset of P, we can write P of A, which equals all Q such that A, for all A in A, we'll have A R Q. Okay, so for example, note Q belongs in RA is the same thing as saying that for all A in A, we're gonna have QRA. Okay, these are the same thing. Okay, so obviously we can find this for all A subset of P of B. Of course, we can do the same for Q. For all B subset for all B subset of Q, we will have that RB equals, we just put it above because like we kind of have a relation where we have A and then we have the B above, right? So here we're just writing the B above. RB will be equal to all P on the side of the P on the left, such that for all B belonging in capital B, P RB. Okay. So, my claim is that our R, if, let's say it like this, if R is a relation on P and Q where they are posets, then we will have that R dot, sorry, is this what I want? Let's see. Yeah. R dot and R dot forms an antitone Galois connection. We also sometimes call this a Galois polarity, I think. If I'm not, or just a polarity, if I'm not mistaken. Okay. Now, to be clear, so the R will be defined just as above, and we have that. So this is our RA. This is our RB. So where R dot below goes from subsets of A to subsets of B, okay, and R dot above goes from subsets of B to subsets of A. That's the domain, okay? I'm not saying anything that required thought. This is just a definition of the function, okay? Now, this is what I'm claiming. This is exactly what I want to prove. This is the interesting fact that I want to prove. I haven't proved it. Let's prove it. Proof. Okay. So we're going to have that R dot below, R dot above forms an antitone Galois connection if the definition is exactly this. If, let me think, if B is a subset of RA is equivalent to saying that A is a subset of RB. Okay. Oh, sorry. Okay, I'm gonna prove a little lemma. Okay. Little lemma. Okay. B belongs to RA is equivalent to A belongs to RB. Okay. Now this is obvious. I can prove it, but it's obvious because the B belongs to RA is equivalent to, as I explained before. But I'll write it explicitly. B belongs to the set of all Q, such that for all A, in A obviously, A R Q. Okay, which is so if B belongs in the set given by this condition, it just means that the element satisfies the condition. So B is such that for all A or B, obviously, okay, which implies that for all A, or it's the same thing as A. So ARB is the same thing saying that A belongs in sorry, RB, okay, which is the same thing as saying that A is a subset of RB, okay? Now what I want you to notice is, like, we have to prove this statement here for where B and B, where it's a set, okay? But I just proved a lemma where B, it's the same statement, but B and B are not sets, they're elements. Well, it's a set, but it's a set with one element, okay? So I just have to prove that if it's true for just one element, then it's also true for sets. Okay? We're going to use this little lemma to continue our proof. Okay. Okay. I'll just continue with this thought that I left over here. Okay. Now, wait, let's start. Let's start here. If B is a subset of RA, it's the same thing as saying that for all B is a subset of RA, where exactly, okay, which is equivalent by our lemma. We're going to use this lemma, which is equivalent to for all B, A is a subset of R B. But actually, that's not very useful. I changed my mind because now it's gonna be a bit of a pain. We can transform this B into a set, but we would like this B to be B. So, I mean, we can do another obvious thing. Instead of decomposing B into little b's, we'll just compose A into little a's. Okay, let's rework our proof. Okay, we decompose this thing, but for the a's. Okay, for all A, we're gonna have that B is... Actually, this is a bit problematic as well. But you know what we should do? We should just decompose both. Let's do that, okay? Now we know that this means, well, I can decompose it part by part. For all B, let's do it, okay? This means that for all B belongs in RA, okay? Which is equivalent to saying for all B belongs, B is related to, A is related to B, okay? For all B and for all A is related to B, okay? Which is equivalent to, we just kind of see it. So you notice that this is symmetric, right? This cannot give us different results depending on whether we start with B or we start with A, okay? So we do this step, but in reverse, okay? So here we don't have any A, so what we're gonna do is the opposite. We're not gonna have any B here, okay? So for all A, we're gonna have that A belongs in R of B, okay? We're just doing the same thing in reverse, which is the same thing as saying that A, big A, is in RB, okay? Notice this nice symmetric way of writing both of these, let's call them inequalities, okay? It's very, very nice and very symmetric. That should tell you what this is, just the same thing. Let's even color it because it's nice, okay? Okay, how about yellow? Okay. But anyway, we proved that. It's proven, we're happy, we did what we wanted to do. Let's put a little square, boom. Sorry, a little square. No, should I add a little corollary? Okay, let's add a little corollary. Okay. Now we know from Galois theory that if we have an adjunction, say alpha beta, then we will have that for any like triple composition, you can reduce it to a single element. Okay, you can basically cut this out or cut this out, same thing. Now this applied to our elements will give us that R composed with R has to be R. Okay, this is our corollary. Obviously, here I started with dot below, dot above, dot below, but I could have started with like dot above, dot below, dot above. Okay, and then I would end up here with a dot above. But anyway, it doesn't matter. Oh, I find this statement very, very interesting. Okay, because it says that like, for example, let's choose a specific example. This means, well, it's a bit chaos, but let's write it out. So this says that like R of A is equal to, let's slowly write this. This is the first R and the second R. Okay, and then it's R R of A. Okay. This is very interesting. And when imagine that, for example, the relationship we have is S is a student of a teacher. Okay, and then we can have S is a student of a teacher. Okay, where this means that all elements of S are students of all these teachers. Okay. Now, this assertion here means that, like, imagine that S is students. Okay, this means that teachers, we should even change it. This means that the teachers of all the S, the teachers of all the S, which I'll just say the teachers of S. So the teachers of S are the same as the teachers of the students of the teachers of S. It's more interesting in this direction. So the teachers of the students of the teachers of S are exactly the teachers of S. No more, no less. That is not obvious. That is not completely obvious, at least to me. Okay, it's very interesting. Given any relationship we have this. There's also, like, for example, in algebraic geometry, we have, for example, the relationship of a polynomial has x as a 0, and sometimes we will basically write z of p to be, well, given this relationship, it would be all the zeros of the p. Okay, and then we can also write the ideal of x, which is gonna be all the polynomials that have x as a 0. Okay. Obviously, we can extend this to sets, as we talked above. And what we're gonna have is this equality. By applying our corollary, and we know that this forms a Galois connection because it comes from a relationship. It's immediate. That's exactly what we proved. So what I'm saying is, like, we're obviously going to have like r dot and r dot. So the thing we have to notice that z is simply equal to r of p, and I is simply equal to r of r of x. Okay, so our corollary will tell us something that should be obvious if we know how to work with Galois connections. That z of I of z equals to z, and I of z of I equals to z equals to I. Okay, that's pretty cool. So basically we're saying that the zeros of the, let's call them the annihilators, I don't know if that's the correct expression, but the zeros of the annihilators of the zeros of a set of polynomials, which would appear here as an argument of a set of polynomials, the same as the zeros of the polynomials. Okay, and the ideals of the zeros of the ideal, or annihilators, the annihilators of the zero, the annihilators of a bunch of points, the same as the annihilators of those points. Okay, pretty cool, but very trivial, but also very nice to keep in mind, because like relationships are everywhere. Binary relationships are everywhere, and it's very natural to think about basically the sets of all elements that are related to some other element. Okay, so what we did here is any relationship we that's defined between points of P and points of Q. Okay, we can write this fancy function that gives all the related elements in the other side, but it's pretty useful to extend this function on elements to a function on sets. Okay, and when we do so, we obtain a Galois connection, okay, which gives us cool things such as this, which is a corollary of the theory of Galois connections. Obviously, we also get the other ones. We have basically that it's has a base like the Galois relation. Basically, you can swap R and R below and R above in an inequality. It also means that we know that R below and R above are both antitone. We also know that R below and R above are both, and R above composed with R below are both increasing functions. So below composed with above and above composed with below are gonna increasing in a certain sense that are gonna be inflationary. Sorry. We're gonna know that this is gonna be greater than this. Okay, that's all. That's the video.